The ever-rising demand for power has led to big advances in the storage and conversion of electricity to better match energy sources with energy consumers. But challenges remain. Now researchers at United Silicon Carbide and Sandia National Laboratories have combined advanced materials with novel manufacturing ideas to build a new product for significantly more efficient power conversion.
I think it solves an enormous problem of improving the efficiency of power generation and power conversion. And I think it's a first of its kind device, a device that actually operates at 6.5 kV at 200 degrees Celsius. I think it's just been a tremendous technological achievement.
You can stack batteries up now to much higher voltages with a switch like this. It's a lot of time in the foundry, working with the engineers and going through just the recipes and everything hands-on. So this was not a process where we just said, please make this for us. We have people stationed there every day looking at the tools and getting it right. And I think that was the key to making this work, was really being inside there and making it happen.
Conversion comes into play because electricity needs to be high voltage for transmission and lower voltage for businesses and homes. And to better utilize variable renewable energy sources, storing and then transmitting that power when needed also requires conversion.
The thing with integrating energy storage and photovoltaics, for example, they are direct current or DC. There's incompatibility there. And you need a power conversion from the DC direct current to alternating current. And that's where the black box or the power conversion system in between is very critical.
Present conversion systems are large, costly, and generate a significant amount of heat. That's where advanced materials such as silicon carbide come in, a transparent wide bandgap semiconductor with superior electronic properties.
There's always room for improvement. Silicon inverters are excellent right now, but they can be that much better with not just silicon carbide, but with gallium nitride as well. Fundamentally, we need to move into a new technology, a new material system that gets us that much closer to nearly 100% efficient power conversion.
This technology takes the current power conversion system that is silicon-based, orders of magnitude more in terms of the performance, the reliability, and the cost of these systems. And it makes the energy storage and renewable much more accepted and available for industry and for public use.
The power switch module is based on a silicon carbide junction field effect transistor, or JFET. Because the switch contains only silicon carbide devices, it can sustain high temperatures and harsh environments, which translates to lower cooling requirements and cost savings.
What you see here on this first row of switches here are the JFETs, and these are the high power leads, and these are the gate leads that control the JFET transistors. And the second row of chips you see are the JBS Schottky diodes that provide for reverse current. So this one half of the module is one switch, and the other side of the module is another switch, and it's a half-bridge configuration.
The fundamental switch device is a 6.5 kV rated enhancement-mode transistor. As a normally off device, no current flows in the absence of voltage on the gate, critical for high-power systems to start up safely and withstand failure modes.
This is very important because the normally off requires a lot more detailed processing to get right. And the high yield process for the normally off device is critical. So this represents the world's highest voltage rated normally off silicon carbide JFET based module.
The voltage level and the normally off solution is the biggest thing as far as the aha moment of this particular switch. And in addition to that, it is in a module, half-bridge module that's available to manufacturers to easily integrate that into their system.
There are multiple challenges surrounding silicon carbide, and a high-yield process has eluded many in the advanced material community. United Silicon Carbide attributes its success to the partnership with the Department of Energy and Sandia Labs, years of research on the initial device structure, hiring the right team of experts, and taking a non-traditional approach to manufacturing.
We've gathered a very talented group of engineers who are very process savvy, and we looked at the high-end processes offered by silicon foundries, and we were able to integrate our patented JFET process into that. So we just took the top-down approach rather than the bottom-up approach. And we were able to penetrate this field fast by taking this approach, and also utilizing fully depreciated silicon foundries that are in existence and need to fill their fabs with new technology because silicon's moving on to higher diameters.
The team is excited about the potential of the module and confident the technology will improve markets beyond energy storage, including transportation and medium voltage industrial motors, which consume roughly a third of the world's electricity.
The product line has really taken off. The first commercial parts were released this past spring of 2014, and then we have a continuous rollout of new product every quarter right now. The storage application was clearly the driving application for these 6.5 kV JFETs. But the wonderful thing about it is that this product will transition to many other markets.